Welcome to the Center for Excellence in Education's Artificial Intelligence series. My name is Clarine Nardi Riddle, and I'll be your moderator today for this event. This session will focus on definitions of and trends in artificial intelligence, with discussions on the cyber landscape, core challenges, and integral trends in AI, and will comprise 45 minutes of panel discussion, followed by 15 to 20 minutes of Q&A from the audience. In addition to chairing the Government Affairs and Strategic Counsel practice at the Kasowitz Law Firm here in DC, I have the distinct honor of serving as a member of the Board of Trustees for the Center for Excellence in Education. For those of you who may not know, the Center is a 501c3 nonprofit, was founded in 1983 by the late Admiral H.G. Rickover and Joanne DeGennaro, the president of CEE. The center's mission is to nurture high school and university scholars to careers of excellence and leadership in science, technology, engineering, and mathematics. CEE provides innovative programming free of charge for all participating students and teachers. Currently, the center sponsors STEM Lyceums for students, the Teacher Enrichment Program for teachers, the USA Bio-Olympiad in concert with the International Bio-Olympiad, and the flagship Research Science Institute in partnership with MIT. All of our distinguished panelists today are alums of the Research Science Institute. In the first of this two-part series on AI, our discussion will be driven by the following distinguished panelists. We have Shashir Malhotra, co-founder and CEO of Coda, who's an entrepreneur, angel investor, and formerly a leader with Microsoft, Google, and YouTube. We also have Dr. Michael Mitzenmacher, professor of computer science in the School of Engineering and Applied Sciences at a Harvard University, and he was also the winner of the 2009 ACM Sibcom Test of Time Award. And Dr. Jesse Rosenberg, science program manager and AI researcher at IBM, who was also named to the Forbes 30 Under 30 list of innovators in science in 2011. They are clearly all leaders in their fields, and we are so grateful to have them with us today. Before I turn it over to the panelists to kick us off for this afternoon, as I mentioned, today's session will feature a Q&A session. Should you have any questions for our panelists, please do submit them to the chat during the program, and we will try to address as many of them as possible in the latter part of the program. So without further ado, Shashir, would you please begin?
All right. Hi, everyone. Good morning. Good afternoon. I'm Shashir Malhotra. Thank you for the great introduction. So I get to kick us off today, and maybe I'll just start with a little bit of my history and particular background with AI. I am currently the founder and CEO of a company called Coda. We make a new type of document. It blends the best parts of documents, spreadsheets, presentations, and applications into a new surface. A lot of our best users like to say that it allows anyone to make a doc as powerful as an app. Before starting Coda, I spent about 6 years at Google, most of the time responsible for the YouTube group. And I arrived at Google and YouTube in about 2008 and drove the division until about 2014. And I think most of what we'll end up talking about here comes from that period. Before that, I also spent time as was mentioned in roles at Microsoft and at starting a company called Centrata before that. But today, we're going to mostly focus on a story from my time at YouTube and a place where I learned a lot of what I now know applying artificial intelligence. So I pulled a couple slides from a talk actually I give at Stanford. Let me pull this up here. And the broader topic here is what's called a human look at AI, but I thought I'd start with a fun story. So this story starts with a dinner prompt. There's a kind of semi-famous dinner here that's run by Reid Hoffman, the founder of LinkedIn, where he picks different topics. He invites 10, 15 different people, and he picks different topics for each dinner. So the topic for this dinner was, we were all asked to suggest a science fiction book that hasn't been written today, but should be written. And the general idea is that most of the science fiction books we read were written, 5 or 6 decades ago, predicting what we see today. But what should we be writing now to predict what we should see 50 or 60 years ahead? There's a great set of people, including many people who are actual authors, unlike me. But I came up with a story that I thought was pretty fun to share. And I was going to pitch you what that book is. And we'll use that as a way to understand AI. So this, these are some of my favorite AI books on my shelf. But the book I pitched is a book I call Tuners, and it's a tragic AI love story. Okay, so I'll give you a little bit of background on the idea for this book by telling a little bit of a story from YouTube. So, and we'll get back to Tuners in just a second. So back in about 2010, we had this, we built a system we call Dallas, a dynamic ad load system. And it started with a really simple idea, this idea of when should you see an ad on YouTube? So when you think about YouTube, you probably think of many different machine learning systems and AI systems. Probably the most famous is the ones that recommend you which videos to watch. But I'm going to tell you a story about a much smaller one, and then we'll talk about the book. So you're watching YouTube. Sometimes you see an ad, sometimes you don't. Why? Well, it turns out that for a long time, we used to do this contractually. So when we would license content from a network, from CBS or from a creator, we would negotiate with them how often an ad should show. And interestingly, every creator thinks their content is the best. And so they would negotiate for smaller and smaller windows. And so they would say, I want an ad not every 7 minutes, but I want an ad every 3 minutes. Or ESPN famously told us they want an ad every 30 seconds. And it took us a while. And it was very frustrating for our team, for our users, and so on. We had this long list of contracts. And one of the engineers said, hey, I wonder if I could design an AI system that would decide whether or not to show an ad to a user. And you might ask, how is it going to decide? I said, well, what it'll do is at that moment, it's going to try to predict whether or not showing an ad would more benefit the watch time or the revenue of the property. To think about it another way, it's going to say at that moment, it's going to say, what is the chances that if I show this ad, this person is going to leave, in which case they're not going to watch any more videos, or they're going to stay, in which case we'll collect revenue from the advertiser, pay it back out to the content producer. So we call this system Dallas, Dynamic Ad Load System. And the way systems like this get built, big team of engineers, and then there's an operator. This operator is a person I like to call the tuner. So in this case, it's a guy named Alexi. And Alexi comes to one of our reviews as he's building the system up, and he says, hey, before I get too far into the system, I need to know what my trade-off function is. You might ask, what's a trade-off function? He says, well, at every moment, I'm going to have to make a decision. Do we show an ad or not? I'm going to take this AI system and I'm going to tune it. I'm going to adjust it until it performs at that barrier. And so we had a philosophical discussion about how much watch time are we willing to trade off with how much revenue. After a lot of discussion, we arrived at a 2-to-1 ratio. And we said, well, we're willing to trade off 2 points of revenue for 1 point of watch time. You can ask, why not 3-to-1? Why not 4-to-1? Why not 1-to-1? It's actually kind of part of the story, is we just decided 2-to-1. So he says, okay, fine, that's all I need to know. And he goes off to go work on building up this system. You might think about it as, we said anything in these shaded areas is okay. If you can produce those results, it's okay. So he comes back a few weeks later and he says, okay, I'm ready. I have my first experiment. I need permission to launch. Here are the results of the first experiment. It turns out it's positive on both. By running this system, we are not only going to increase how much money we make, we're going to increase how much time people spend on YouTube. No, super interesting. So the obvious question, why? He said, I have no idea why, but that's what it is. Can I launch? Lots and lots of debate. Why is this happening? Doesn't make intuitive sense. And we say, okay, Alexi, you can launch, but you have to come back next week and explain why. So he comes back the next week and he says, well, I have good news and bad news. Good news, tuned it again, even better output. We're getting even more revenue per point of watch time, but I still can't explain why. And this happened week after week after week of him coming back with better and better results of watch time versus revenue, and this sort of inexplicable balance of sort of getting our cake and eating it too. Now, after a few weeks, we did figure out why. And it turned out what the system had learned was it had learned that if it pushes ads later in people's sessions, then we could both make more revenue and make more watch time. And to put it in more human terms, if you think about it as, if you're watching YouTube and it's the first time you've ever watched YouTube and you're on your very first video and you see an ad, it's very likely to spook you away. But if you've been on YouTube many, many times, you come every single day, you're 3 hours into your session, chances are ads aren't going to spook you away, and you might enjoy them in that experience. We could have started with that insight and said, what if we just push ads late in the session? I wonder if we could both increase how much people watch YouTube and how much revenue is produced. But we didn't figure that out. The algorithm figured that out. It learned through this system. Okay, so here's the book idea. So the book idea is a futuristic setting 50 years from now. And in this world, there is a series of job functions called tuners. And these are people that run these AI systems. Not the researchers like Michael and Jesse we're going to hear for a moment that invent AI systems. They're the ones that run them. They're almost a little bit like, if you think about it with white collar and blue collar jobs, they're almost the blue collar operators of that industry. And in this story, there's two of them. One of them works in the HR department and the other one works in the food department. And the HR department tuner is responsible for the system that helps figure out who gets promoted and who doesn't and who gets what compensation and so on. And the tuner in the food system helps figure out what recommendations to make for what people should eat. So, this advanced company has sort of figured out you get a custom lunch pack and a breakfast pack and so on when you get to work. These two start dating. It's a tragic love story. It turns out that their AI systems are being tuned against each other. And what the HR system has figured out is that it's very hard to fire people, but if you give them the food that makes them a little bit sick, then they kind of tend to quit on their own. And the system learns and learns and learns, and slowly these two systems start killing off the employees. Okay, so that sounds really dystopian. Sorry to start your morning or afternoon with the dystopian version of this, but I think it's kind of a fun way to think about a couple different lessons from this story. So first off, three lessons that I wanted to leave from the story. So first one is, I actually don't have a dystopian view of AI. I'm actually quite optimistic about AI. I think AI is ever present in our lives. Like I said, most people think of YouTube as having a single AI algorithm. Actually, just YouTube by itself, we had 100 different machine learning systems that did everything from deciding what to recommend to you, when the ad should play, who gets paid out when, what thumbnails should be shown to people, all these different systems everywhere that help make these decisions. And I think many people don't realize how much AI already surrounds us. It's what allows us to find great videos to watch and books to read. It allows planes to stay in the air. It allows traffic lights to change on time. It allows packages to get to us in this mind-boggling speed from around the world. All these things are created by AI, and it actually is very ever present. The second thing I would take from this lesson is AI systems versus AI operators. When we talk about AI systems, we often talk about the people who build the algorithms, but actually much of the interesting part of how AI works is in the operator, what I like to call the tuner, the people that actually take those systems and apply them to a problem. They give them the right set of data, they get them the right set of goals, and then they help adjust them as they move. And this role of tuners, I think, is one that we don't talk about enough when we talk about AI. And then finally, thinking about segmenting AI, oftentimes we refer to AI systems as a system that, given an input, it will recommend an output for a particular goal. So you can tell it, I want more watch time, I want more revenue, I want the traffic lights to change on time, I want packages to get to me on time, whatever that might be. But one of the things that has happened with AI is that the systems that have tended to do best are the ones that we sometimes refer to as black box systems, or the unexplainable systems. So if you take AI and split it into explainable and unexplainable, some systems, you know exactly why a recommendation is being made. In other cases, you actually don't know why that recommendation is being made. It's actually a feature, but it's considered a feature, not a bug, that the system has figured out something about the world around it. It's figured out, you know, how to recommend food to people, or it's figured out where to place ads in a way that could have unknown outcomes. And I think that's one of the most interesting questions facing AI, is how to adjust our world to running on so many systems for which their behavior is intentionally unexplainable. So I thought I'd start with a fun story. And like I said, the book idea is a little dystopian, but I have actually quite optimistic view of AI. And we'll talk more about that in a bit.
Hello, I'm Michael Mitsumacher. I'm a professor of computer science at Harvard University. I've actually been there since about 1999. I am not specifically an AI researcher, or at least didn't grow up that way. I grew up, you know, coming through theoretical computer science primarily, so that's the more mathematical end. And most of my work involves algorithms and data structures for information and communication. At the low end, I like to say, you know, at the very low end of information, I look at things like how bits are sent over, you know, say the current 5G networks, how you might use encoding, for instance, to protect your data as it's going through the wireless network from losses or from corruption. You know, and at the very high end, I think about things like, well, how is it that companies like Google, you know, you just type a word or two in their search engine and they're suddenly able to gather and present to you large sets of relevant documents. So I come from that sort of background, and I find more and more these days that what I'm doing is AI, not necessarily because what I've changed, what I'm doing so much, but just everything these days is now AI because it's such a booming industry, such a large part of computer science. And so now I'll share my screen a bit. I just wanted to give some examples of that. So, you know, I'm Michael Mitsumacher at Harvard University, and how do I relate to machine learning? So, like I said, I work on algorithms and data structures. So, you know, I'm sort of looking at these high-level issues of how can algorithms improve machine learning and machine learning systems, and also sort of the other way, how can machine learning help or improve algorithms? And let me give, you know, sort of a brief example of each of those. And I'll start with the second one, like how can machine learning improve algorithms? And so one of the problems I work on involves scheduling. So scheduling systems, right? So, you know, queues are just lines. How do we, you know, deal with the fact that, you know, people or jobs in our computer systems have to wait in line before getting processed or before getting done? And what can we do to make that process better? So, you know, in a typical system, like if you go to, you know, a bank or a supermarket, you know, maybe the lines is just a simple line. You know, you get in line and you wait. It's first come, first serve. You wait your turn. You know, in terms of efficiency, you know, this isn't best. You know, maybe you'd call it fair in some metric. You know, you get in line and you get your position, and that's, you know, fair in the sense that, you know, it's based on your arrival time when you get served. But it's pretty unfair, unsatisfactory from the point of view that, you know, maybe I just have a really quick task that just needs a minute of time, and I'm stuck behind someone in line that's going to take a half hour and make me wait, right? So there are better systems. If you're trying to minimize the overall time that people as a whole spend waiting, you could do better, right? You'd put the shortest jobs first. So, you know, the non-preemptive version of this, where just like once you've started service, you continue through service, is the shortest job first, right? Whoever has the shortest job in line, you get to go next. The preemptive version of this is shortest remaining processing time. So what preempt means is maybe you're getting served and then someone comes in and interrupts and says, wait, I just have a 10-second thing. You go ahead and handle that person's 10-second thing and then come back to you. Okay. And perhaps not surprisingly, these sorts of scheduling systems have been, you know, are known and well studied, have been around in the literature for rather a long time. Right? But strangely, as I started to get into this issue of, how can machine learning improve algorithms? What I've found is that people have done very little work or minimal work these days on what I would call sort of the version of this where you have predicted service times. And so the idea here is maybe you have some sort of machine learning algorithm that predicts the times the job is going to take, or how long a person in line is going to take, right? And so you can say, well, what if I consider the predicted versions of these policies? I'll do the shortest predicted job first, or shortest predicted remaining service time. And these certainly make intuitive sense, but you want to ask sort of theoretical or framing questions of, well, how well can we do with predictions? Like, how good do predictions have to be to get a certain amount of gain? How do we avoid sort of the problems that if predictions are poor, because our systems are not always going to work or function the way we might like? What we're aiming for with these sorts of systems, this area is actually relatively new and just a few years old, I'd say, and is called an example of algorithms with predictions. And what are the sorts of things we're looking for when we're working with algorithms with predictions? Well, I being a theoretical mathematical person, I'm trying to prove things. I'm trying to formalize and say, if you give me a good enough prediction, I can guarantee this sort of outcome, right? So this gets into the question that was raised previously, which is like, well, some systems aren't designed to necessarily tell you, well, why is it you're getting a good answer? And the idea is that, well, regardless of how or why it's getting that answer, what I'd like to do is give some sort of guarantees. If you give me a good enough prediction, I can guarantee this sort of performance. So the things that we're looking for, the terminology we use is we're looking for consistency, for perfect or essentially or perfect or near perfect predictions, you'd like to get near optimal performance. Graceful, as predictions get worse, your performance will clearly also get worse, but that performance degrades gracefully. And robust, in that even if the predictions go completely wrong, right? Even if your prediction system, your machine learning system breaks down, your performance doesn't just fall apart. All right, so while I am here, before I go on to the next part, I'll give a little plug. This is a book I have that doesn't specifically talk much about algorithms with predictions, but it has a lot of the probabilistic and computing background. Again, a lot of my work on information communication relies on probabilistic tools, and I have a book that covers a lot of these tools that I found very useful in exploring these sorts of problems. So another problem, now going the other way, right? How can algorithms help machine learning? So there's an area called federated learning. And the idea here in federated learning is, all of us may have some sort of app or program running on our device that has, some sort of machine learning model embedded in it. And, there's some central server that's maybe getting updates from our devices, and it's using that to continuously tune and improve the model. So it's getting some sort of information back from our phones. That information, I'm showing it as a very large vector, right? You can see up at the top of the top phone here, I've got this vector of real numbers. You should think of that vector as being hundreds of thousands or potentially millions in length in terms of numbers. And what the central server does is it gathers information over time from some of these devices and then averages them and updates the model. Okay. And so here we're talking about very large numbers of devices, very large sets of information that need to be sent. And the question is, how can we reduce communication as a bottleneck? And now this becomes an actual algorithmic and data structure problem. Okay. And so this is an area I've been working on using tools in compression and approximation, right? So we don't necessarily send, we're not going to send all the entire list of numbers. We're going to try and compress it down in some way. And in particular, we're not going to worry about sending the exact vector, because at the end of the day, what we need our server to do is come up with a good approximation of the average of the devices that it's getting information from. It doesn't actually have to be the true average to be successful. And so we can utilize compression and approximation to greatly reduce the amount of communication. So in fact, we've shown that there are very good schemes that instead of using, sending these real numbers, which can take 32 or 64 bits per entry, we can get very good schemes at even just 1 bit per entry or even less. So again, to summarize where I come in or how I see these issues is that, I'm looking at how algorithms can improve machine learning and how machine learning can improve algorithms. And I sort of view machine learning and AI generally as sort of a new tool set or something that can improve, our processes, our systems, and how they function.
All right, great. So I'll take over now. So I'm Jessie Rosenberg. I'm the Science Program Manager and Strategy Lead for the MIT IBM Watson AI Lab. So I think it's great that I'm talking, after Shashir and Michael. I think my organization sits a little bit in between both of those efforts in that we combine some industrial work as well as academic work. So I actually work at IBM, but my organization does collaborations between IBM and MIT. So we sit sort of in the middle range where we're doing some basic research, and then we're also looking for applications. So I'll just share my screen here. Yeah, so a few years back, IBM did an analysis of where we see what's the future of AI going to be like, and I think this still holds true in that in the past few years, and as AI has grown, it's been relatively narrow when it started out. So you would have AI applications that would work maybe for one specific thing, like you can recognize melanoma in images of skin, or you can do a recommendation system for one particular type of movie or maybe one particular application. You can recognize cats out of a set of images. You can distinguish between cats and dogs. So that's where we started. And then we figure as AI continues to develop, and especially we're sort of at the border of these two regions now, AI is infiltrating, shall we say, all aspects of life. I think just going about our daily business, as Shashir was saying, AI is pretty much everywhere. It's doing our routing as we drive to work. It's recommending what movies we should watch, what books we should read. It's generating text out in the wild. So it's really throughout our lives. And then this column on the right, what is general AI? What is general intelligence? This one is a little bit harder to describe what that will look like. But in this analysis, we pegged it as 2050 and beyond. And I think many people you would talk to would say the same thing. And I think when you say 2050 or beyond, that just means kind of some undescribable time in the future. So what I think is the most interesting right now, and what my organization focuses on, is this broad AI regime. How can we take AI from the original narrow applications that they started out and make it more broad, so able to handle different applications gracefully. So narrow AI, single task, single domain. Broad AI, which is this is really where we're moving into now. AI that can work on multiple tasks across multiple domains. Domain being like it could work on both audio and text and video and images. And that this explainable piece as well really comes in the concept of broad AI that Shashir talked about, being able to understand why do these models do what they do. Because, for example, this is an image of a surgical robot. If you're having AI involved in all of these critical domains, you really need to understand why it's doing what it's doing, because you need to confirm that it's doing the right thing. And then, when we move into general AI in the future, that'll be when it's really fully cross-domain, when something can work autonomously, really in the same way as humans are. So how do we see the path to broad AI? And there's a number of elements that we think come in there. Explainability is a big one. Why does it do what it does? How much can we understand, and also justify what our systems are doing, so that and how can we even constrain them, so that, for example, if it's working in a safety critical application, say you have an AI system running a factory, we need to understand why it's doing what it's doing, so that we can constrain it to only take safe actions. Security as well, so robustness against adversarial attacks. You may have seen some of these examples out in the news in the past. It is possible to generate, For example, by putting the sticker on a stop sign, you can trick some black box AI models into thinking that in fact it's a speed limit sign. So robustness goes back to explainability as well. And similarly with ethics, you want to make sure that your systems aren't biased, that you're treating similar people, say of different characteristics, similarly, where those characteristics don't impact the downstream task. For example, providing loans or mortgages, we want to make sure that our AI systems are not prejudiced when they take those actions. And then going forward, being able to apply AI more broadly, we also need to handle the cases where we don't possibly have a fire hose of data. Maybe there's some cases where we only have a few examples. How can we generalize? A human baby, if you show them a picture of a zebra, even maybe a single one, they'll learn, oh, that's a zebra, and they could see that zebra again, even if it's a different picture, and they'll know, oh, this is a zebra. So how can we learn from very small amounts of data, generalize and categorize? So that can come possibly from transfer learning, so taking one AI system and adapting it to work on another domain, or potentially, or maybe combining both of these things, is including reasoning and existing human knowledge. So there are many situations, things like the laws of physics. We actually know, we can write those down. And so rather than having to say, have a million videos of a ball bouncing in order to train a model that can predict what will happen when you drop a ball, we can make these systems much more efficient by incorporating knowledge that we already know, in this case, the laws of physics. And not just incorporating existing laws, but then learning these laws. So how can we take a set of behavior and distill that down into the smallest possible description? For example, discovering the laws of how a ball bounces, even if we don't provide that from the beginning. And again, many domains have this type of reasoning that a human would do automatically. Like, oh, if I'm an air traffic controller, I don't want the planes to hit each other. You don't necessarily need to be taught by 1,000 examples. You just know that that's the rule. And then, to support all of these applications for broad AI, there are developments that need to be made in infrastructure. So physics of AI, so actually optimizing our computer systems in order to better suit AI applications. And then also platforms for the full life cycle. So how do we provide compute? How do we store data? How do we trust where our data comes from? How do we share our data in a safe way, as well as our models? And then the full workflow of developing an AI system. So how does development change when I, as a software engineer, I'm not just writing fixed code, I'm writing fixed code combined with some, say, learning code. How do I best incorporate those learning and changing elements into my existing code base in a way that I can still predict its behavior, test its behavior, make sure that it does what I want on the cases that I'm designing it for. So these are kind of a broad spectrum of topics, but I know this is the session on trends in AI. So these are some of the trends and special topics that I think are important. And if I have a minute, just quickly, the way that our organization works, this is one way that we do research, is we combine between IBM and MIT. So IBM provided an initial investment to start the lab in 2017. And we have projects that are joint between industry researchers and academic researchers, which I think we're a fairly unique organization in that sense, that all of our projects have a leading researcher on both teams. And this results in many publications. And as well as working with other industry partners to join in our research and to focus on their target applications. And for our portfolio, we cover a number of topics. Again, these being what we think are our main target areas. So base foundation models, say language models or vision models that are used across the industry, or fluid intelligence. So this is what we would call moving towards broad AI, having systems that can operate not just in one narrow domain, but across domains, across modalities. For example, a robot that can both speak to you and track down an object in your home and cook you dinner. These are all separate tasks across separate domains. How can we trust AI? How can we make AI more efficient? So there's a whole climate aspect. As our models get larger and larger, just being able to train them takes up a significant amount of energy. So how can we do that more efficiently? As well, using AI to actually improve science. So targeting new material discovery, climate, physical applications, industrial applications, such as, again, running factories, and then also improving businesses. So I'll stop here and send it back, but I think we'll have questions later.
Well, wow, what wonderful, thought-provoking presentations. For the audience, we're going to have a little discussion among the panelists, and then we will go to the Q&A period. Okay, Shishir, you talked about artificial intelligence, but what is it exactly? How do we explain this to the audience?
So my father is a computer science researcher and professor as well. And when I was growing up, and actually maybe it's just context, the concept of AI dates back to the 1950s. So it's something we've been talking about for a long time. When I was growing up in the 80s and 90s, AI's reputation was nearly the opposite of today. So when I'd ask my father about what AI was, he'd say, "Oh, it's all the stuff that doesn't work. At the moment anything actually works, we no longer call it AI." And that was kind of the reputation it had for a long time. As Jesse described, narrow AI was sort of the moment you understood the magic, it no longer felt like magic. And if we take a very broad definition of AI, I think it is a system that, given a set of inputs, it'll give you an output that is designed to influence a particular goal. So it's an input, an output, and a goal. And so if you took a simple example of you pull up to a traffic light and it makes a decision about whether it turns green or red or how fast it does, a really simple algorithm would say, if a car is present, wait n seconds and then turn green. That doesn't really seem like AI. It just seems like a rule. It seems like but if you said something like, every day, watch how long it takes for that car to move and then change it, that kind of like starts to feel a little bit like AI. Similarly, if you look at a system we're all used to relying on in an airplane, the autopilot system, if the autopilot system were described, just make sure to move this one thing up and down to keep the airplane at this level and even in the air. That doesn't really sound like AI, but if you sort of broadly describe it as, given anything happening around it, produce the set of outputs for these set of tunings to keep the plane at this altitude and this level, all of a sudden that sounds a little bit more like magic. But I think the broadest definition of AI, I think, is given a set of inputs, give me an output to try to achieve a goal. And there's lots of dimensions of that people then break apart. Is it a learning system or not? Learning systems are ones that, given new past predictions, I gave you an input, it gave an output, it didn't achieve the goal, or it did achieve the goal. Learning AI systems take that and reincorporate it to try to do something different the next time. There's sort of many different definitions, and Jesse talked through some great ones, explainable versus unexplainable and so on. But I think that's my sort of broadest definition of AI.
Thank you. Michael, how do you teach Lucy there in your classroom what an algorithm is, and how do algorithms relate to AI?
So I always say, like, the way we typically think of an algorithm is like a recipe. So just like you would say, well, I want to bake a cake. So I've got, eggs and flour, and I've got directions that tell me how to mix them. So I can take these inputs and produce an output.
Mm-hmm.
And that should probably sound very similar to what Shishir was just saying, right? So one way of thinking of AI is that it's a set of algorithms. Again, it's taking in, you give it an input and it's producing some sort of output. And the output is designed to, the way I might describe it, is to optimize some function, right? There's something that's trying to be optimized and it's trying to give you the optimum. Maybe the difference or the, there are certainly, you could say algorithms for AI, and as I've described, using AI for algorithms. I think sort of the difference is that often in algorithms, we think about, things that always work in the worst case, right? We're saying like, here's the input, there's some right answer, and we're going to guarantee that you get that right answer. Okay. Whereas the machine learning is, again, it may not necessarily have those sorts of guarantees. And it's also, instead of thinking of it, specifically about, okay, I've got a problem instance, like I want to find, the shortest path that will get me from, Boston to New York, because I've got this drive I want to do, right? It not only is it that I may not, necessarily get the right answer, but that, the way it's doing this, the way it's judging this is based on a lot of external or historical data, right? It's using that extra additional information to try and make these sort of predictions about the future. So that's why, for instance, an AI algorithm, instead of just trying to calculate the shortest path in terms of distance, might be able to say, well, based on historical data, if you're leaving at this time of day, this is the best route to go based on traffic or other things that might come into play.
Interesting. So, Jesse, how powerful is AI? Is it going to be taking our jobs? Are we going to all become tuners, or are we going to not be able to become tuners?
So I would say, looking into the future, I think AI will impact, many jobs just as it impacts our lives. But the question, will it take our jobs? I mean, I see like not in the near future, at least, not every job, at least, because there's a lot of things right now that are still challenging for AI. So looking again in this kind of broad AI, moderate term future, AI can solve a lot of problems. It can solve a lot of problems even better than a human. For example, recognizing melanoma, or maybe recommending what video I myself should watch, unless there's somebody who's dedicated to that job of recommending videos for me. AI is going to do a better job at that. But there are many things that it can't do. So for example, even playing chess, AI can play chess very well, but still humans together with AI, at least last I heard, do better. So there's a lot of things where humans and AI, when they're combined, can cover up a lot of the faults of one and the other, and do things even better. So I think, looking into the future, there are too many domains where, again, the AI is still a black box. It can't explain what it's doing. We can't always be sure that it's going to do the right thing. And in those circumstances, we'll still need to have humans to assist and guide and also train these systems. So I call it jobs will change in some ways, but certainly not go away. And I think in many ways, they'll be much more rewarding because a lot of the rote work can be handled by systems, leaving humans to do kind of more interesting and cognitive things.
Wonderful. What do, I'm thinking of the students in the audience who are listening and thinking about their own careers, and, what do careers in AI look like? What background knowledge is helpful? How does someone get started in this field? Shashir, you want to take that? You've done so much.
I think one of the observations probably from all the talks is that AI, I think of it as a skill set that will slowly eat into every job. A phrase we end up seeing a lot in technology, that software is eating the world. And to take Michael's observation earlier, AI is eating software. And so it's very hard to find a job these days where technology is not a key piece of it and where AI is not a key piece of that. Yeah. If I were to divide out roles over time, I think we'll see sort of three broad buckets. I think there's researchers where their job is to sort of invent new basic building blocks of AI. I think we heard some really good examples earlier. I think there's a second group that I call the tuners or the operators. That's what the sort of dystopian book is about, whose job it is not necessarily to know much about the system, but to make it do something. And then I think there's the appliers, whose job it is to decide when to apply an AI system or not, and where it should fit in a business flow. I mean, to take the example I gave about when to show ads, I mean, that's something that if you are a contract negotiator for a licensing video for a media network, you might not expect that you're supposed to know what AI can do. But it actually is quite important to be able to make that proposal in the contract and say, how about instead of putting a number in here, we put in place a machine will decide. So those are sort of three different ways I think about it. So in some ways, I don't think you can or should try to escape it. I think it's actually very important to know a lot about it. Not everybody needs to be a researcher. I think that tends to be people are just deeply interested in the science and the math of what's happening there in the systems. But researchers, tuners, and appliers are sort of three different ways I think about it.
Okay. Well, we have some questions among ourselves that we could keep talking about, but we promised the audience that in the last 15, 20 minutes, we'd go to their questions. And so we're getting a nice group of those. And the first one is for you, Shashir. When will the tuners be published?
Yeah, nobody's taken me up on it yet. I actually had at one point my daughter had a friend who actually thought about doing it, and I am actually, interestingly enough, writing a book on a completely different topic, and so I have a little bit of appreciation for how hard it is to write one. But the interesting thing about the question, I think most of the AI books out there are still based on a very different interpretation of either the utopian or dystopian view of AI, and many of them are based off of sort of a viewpoint that the scary or not scary part about AI is when they can approximate humans, which I think is interesting, and it's a fun discussion, but I actually think it's kind of irrelevant to understanding the true promises or dangers of AI. So that's why I was interested in it. But no, it's not on track to be published. If somebody wants to do it, I'm happy to help.
Sounds good. I think this is maybe Jesse kind of touched on this second question from the audience, but maybe you can elaborate more. How do you evaluate the possible bias in the AI algorithms based on the programmer's perspectives and backgrounds? Clearly, this is something in Washington, D.C. that some of the regulatory agencies are looking at. And you mentioned it, Jesse, when you were talking about lending and in that financial services arena. But so people, and yet, it's like this is part of the business now, right? So some more thoughts on that, Jesse?
Yeah, so I would say, one of the interesting and a little bit scary things about using AI for critical applications such as that is, on the one hand, yes, you do have to be aware of the programmer's bias, but even beyond that, you have to be aware of the bias in the data. So for example, if you have a data set where all, purple things are good and green things are bad in your data set, then you will always label that an AI model trained on that data set will always label green things as bad. Even if out in the world, it's actually not true. Maybe it's squares and circles, and there's some purple squares and some green squares. But if your data set is biased, then also your results will be biased. So this is one of the kind of explainable AI areas, robust AI areas that I think is really important. And in ways that you can test that, for example, you can give it a test case, an example. So, in the case of a person, say you give it 2 example people, which are the same in all characteristics, except for one characteristic that may be completely irrelevant to your domain. And one way to benchmark, what is the bias of our AI system is, does it treat those 2 people differently? And this is a really interesting area of study even down to the very fundamental mathematics of how do we create AI systems that actually mathematically can be proven in some way to be unbiased. With these 2 similar people with an irrelevant dimension being different, how do we ensure that they treat those people the same?
Yeah.
I was gonna add one story to this. I think and this is obviously it's something at YouTube we took really seriously, because it's lots of different types of bias you could have in various the hundreds of different ways that we use AI. And over time, one of the things we got most excited about is a concept that's called adversarial neural networks. And the basic idea is when you're training an AI system, sometimes you have explainable systems where you can understand exactly what it's doing, and sometimes you can work to try to explain what it's doing, but oftentimes it's very hard. So sort of the tuner's example I gave. So one of the things you need to do is kind of trick the system to not have bias. And so you can test it in many of the ways Jesse has described. But to use an example of loan applications, a very commonly used example, if you're trying to decide whether or not to give someone a loan, and you ethically would prefer not to have race impact the decision. It turns out it's actually just removing the race field doesn't really help that much, because you can determine a lot of that potentially by where they live, what their income levels are, where they went to school. So there's a lot of other ways to get to that without actually telling someone what race someone is. And so one of the things you can do is you can tune a neural network to give you 2 outputs instead of 1. So you say, hey, I'd like you to tell me whether or not this person should get a loan, but also I want you to tell me what race you think this person is. But I want you to tell me, I'm going to train the system to be very good at telling me whether or not this person should get a loan, and incredibly bad at telling me what race they are. So I'm going to anti-train this whole system so that it actually has no idea what race you are. And this became a very effective technique. The way the question was phrased was bias of programmers, and as Jesse was pointing out, it's not just bias of programmers you have to worry about. And there's the bias of the data set, there's biases built into the systems that you may just not even predict that it's going to find. Like the fact that our system pushed ads later into people's sessions. And so this idea of anti-training became very important. So the finishing that tuner story, when they came back, we had a real debate. Is it a good idea to push ads into late into people's sessions? If we decided it wasn't, we would anti-train against it. And we would say, you're not allowed to train towards that outcome. And in fact, you have to anti-train against it. So it is possible to remove bias from systems, but you have to be clear which bias you're trying to remove.
Gotcha. Wow. Got another question. This one's for Michael. I see that the federated learning system improves scalability. Can you explain some of the privacy benefits of federated learning? In other words, how easy is it to infer an end client's data from their updates?
So I'd say this often depends on the problem or how federated learning is used, and is certainly an area in active research. One of the benefits in terms of the federated learning, like I've described, is that you're sort of gathering information from many people and sort of averaging it out. And one of the benefits of that is that you can get away with needing less information from any individual person. And as I've described, it often suffices to just get approximate information from them, right? So that enhances the privacy, and that you can, sort of the less information you're pulling from any one person, the more their privacy is itself enhanced, because you're not sort of depending on them or depending on their exact information. But yeah, I've actually done some work on sort of the other end of it, where we've been looking at attacks on learning systems and federated learning systems. And it is a worry that when you get something about someone's weights, just by getting information about their weights, how they've responded to certain inputs, you may be able to infer something about what it is they've actually seen, or what data they've been processing. So this is going to continue to be an active area. Federated learning offers some help, but it's certainly not a complete solution, and it often is very problem specific and depends on your security model.
Great.
And
Go ahead, Jesse.
Oh, I just add, there's some mathematical techniques there as well, called differential privacy, where you can add noise, and you can calculate actually the amount of noise that you need to add to specific categories in order to obscure the information, because it is, as Michael said, a big challenge. It is technically possible using various adversarial attacks to actually, just from a trained model, extract out some person's data, if, for example, that person is in a class that doesn't have very many examples. But there's ways, and it's an active area of study, how can we add just the right amount of noise and just the right amount of scatter to make people's data private, while also not degrading the performance of the models too much.
Well, wow, what a set of questions and illuminations, I think, on all of these topics. We've gotten a few more questions about use issues of AI and also regulation of AI. And I'm happy to let the audience know that we're going to have a program just on uses and ethics of AI in 1 week from now, June 16th at 1 o'clock. I believe they'll be putting that in the chat room, the link to the registration for that program next week. I clearly want to thank the panelists today for such excellent, informative, colorful, and helpful conversation of the artificial intelligence talk. And I hope, and I want to thank the entire audience for participating today too. So please sign up for the second of our two-part series for next Thursday on the uses and ethics of AI. That one also promises to be a lively discussion. So have a good day, everyone, and thank you all.